Today, we are really excited to have Gokul Prabagaren come talk to us about financial data with Cassandra. Gokul talked at one of our previous events last year, Indie Cloud Conf, which has since been retired. But it was a really, really cool event, and Gokul is an awesome speaker, and I'm really excited to have him back.
Good morning, everyone. I hope folks are now, what I was discussing with Josh too, adjusting to this new norm of continuous stream of online virtual conferences. I hope we will go back to the in-person events and have some more real networking. Right? I am here to discuss about one of the use case we dealt in our organization as my discussion topic, like modeling the financial data in Apache Cassandra to serve real-time and batch workloads at the same time. Okay. So before we dive into the topic, some details about me. I'm Gokul Prabagaren, engineering manager at CapitalOne. If you have used any of our credit card, if you have swiped, so my team is basically responsible for providing the earn you are supposed to get for whatever the spend you are making on our card. So we are a group of teams which is really responsible for the suite of earn related things on CapitalOne credit card. And I have been building applications from initial versions of Java, and lately I'm doing things on big data side of Apache Spark, and probably from version 1.2 in Java and Spark's initial versions. And my interest is around distributed computing, and I have contributed the various blogs to CapitalOne Medium, and you can find the topics mostly spanning around big data technologies or something on NewSQL comparisons. Those are the things I have dealt in our Medium blog. And I have included my LinkedIn and Twitter handle. You guys can connect me there, and we can discuss about any of this distributed computing or any of this big data things, interesting topics. Okay, so here is the agenda for today's presentation. So I'm not sure the knowledge level of our audience, right? So I thought probably just giving a quick introduction on Apache Cassandra will level set the field so that we can build on top of that, like what is that we want to discuss, right? So introduction on Apache Cassandra, and then we will try to see how it differs from RDBMS, and particularly when it comes to the data modeling, and that forms the core of this whole discussion, right? And how rewards organization, which I am part of in CapitalOne, has leveraged, and what is the high-level architecture which uses this data modeling for its most of the use cases, right? Particularly in this case, how we have leveraged Cassandra's data modeling to solve the real-time use cases as well as batch use cases, right? How these two can be connected together, mainly from Cassandra's data modeling perspective, and solve all your needs. And finally, leaving some room for Q&A. Okay, let's get rolling. So Apache Cassandra is probably one of the top NoSQL database, MongoDB being the other one. These two makes up probably the top 2 or 3 widely used NoSQL database in the market, and they play a major role in this enterprise space. So Apache Cassandra and MongoDB are the top NoSQL databases, right? The Apache Cassandra was initially built by Facebook engineers for their internal need, and then they later open sourced the database. And there is a company called DataStax which offers a commercial enterprise offering on top of this Apache Cassandra. And by now you all may be familiar with all the things which we have from RDBMS side, particularly on the ACID properties, right? What kind of impact it has on RDBMS applications and data store. So ACID property plays a major role in any of the RDBMS, right? That kind of the similar base is what CAP theorem plays in the new generation of this NoSQL databases, which came after the RDBMS era when internet took off, right? So what CAP theorem means, and a CAP in the CAP theorem is expanded into consistency, availability, and partition tolerance, right? What it basically defines is when you will be able to get only 2 out of this functionality when you are trying to span your cluster. And major difference with this NoSQL compared to the RDBMS is typically in RDBMS previous era, it used to be one bulky node, maybe a disaster node we have, but though it typically is one node which takes care of the entire database operations, right? But with the NoSQL, it spans across cluster. That's how it scales, right? So it's not one node anymore. It's cluster of nodes is what makes all this NoSQL offerings when it comes to the database side. So that's where CAP theorem plays a major role. What it states is you will be able to achieve either one of these two from this 3: consistency, availability, partition tolerance. And pretty much the NoSQL databases falls into the category of CA, where it focuses on consistency and availability, leaving the preference of partition tolerance least, right? But Apache Cassandra focuses on availability and partition tolerance and having the consistency as something called eventual or tunable consistency. What it means is you will always have consistent data available, and also you will be able to recover even if one of your node goes down, the partition is not available. Those kind of things takes the precedence over the consistency. But it doesn't mean that you won't get a proper consistent data. It's not like a dirty read or anything, but there is a way in which you can control this. That's what I mean by eventual or tunable consistency. Let's say you are writing some data and your use case to read them immediately. There is a read consistency and a write consistency. And when to consider that your write has really made it, right? But in previous RDBMS case, you don't need to really worry about this kind of things because it's all in the same node. That's what it means by ACID. But here, it's all cluster and there are series of nodes in the cluster. When to consider that whatever you wrote has really made it, right? That's what defines your write consistency. Basically, you say you're writing to one node, I'm fine if only that node gets my recent write, right? That is typically the write consistency of 1 in Cassandra terms. Similarly, you have a bit more strong consistent use cases where you cannot have this kind of dirty reads. Or in RDMS terms, it's dirty read, but here it's like you probably need to have more consistent data. Then you can go for even stricter consistency when you are trying to read, and you can enforce that with your read consistency too. For example, it's local quorum in Cassandra terms, where it ensures that whatever the writes happened, and when you're trying to consume them, you are consuming from the majority of the replicas after it reached in your local data center. Typically, it's a region in cloud terms. That's what the local data center in Cassandra means. And Cassandra doesn't follow primary and secondary architecture. Instead, all the nodes in the cluster take the same precedence. And in case of this primary secondary architecture in NoSQL, if primary goes down, then there is typically an election which happens behind the scene, and one of the secondary becomes the primary and it has to catch up, right? That's what I mean by a single point of failure. In Cassandra, we don't deal with that, and each node in the cluster has the same precedence over the other. So advantage with that approach is you don't have a single point of failure. Columnar storage, right? The Cassandra falls into, there are various types of NoSQL available. Cassandra falls into the columnar storage type of NoSQL. What it means is the data, it persists. Typically comparing with the RDBMS, if you have a row, how the data gets persisted in the disk is you define a key and rest of your columns are mostly the values, and that's how it gets persisted in the disk as well. And that key is typically referred as partition key in Cassandra, and given that key you will be able to pull all the rows. Those are your column data, right? That's how Cassandra stores the data in the disk, and that's what I mean by columnar storage. And Cassandra doesn't have any joins like how we have in RDBMS case, right? So what is the cost of not having joins? I won't say it's cost, but that's the design, right? That's what makes Cassandra a blazingly fast database for any of your reads, right? The suggestion there is you need to denormalize your data and you need to duplicate your data. What that means is probably you may need to keep the similar columns in multiple tables, and also you need to duplicate your data as well, right? Because you don't have joins, you need to denormalize. And depending on your use case, you may have to duplicate your data too. And that's what we are going to discuss more in our upcoming slides. The main core difference when it comes to the Cassandra and RDBMS is use case based data modeling. And that's our core topic of discussion too. And we will see about that in the next slide. Okay, as I previously mentioned, where Cassandra majorly differs from RDBMS is in its data modeling and how your use case basically defines all these things. Right? In a typical NoSQL, I mean the SQL RDBMS world, you define your table schema, and mostly your application adheres to the table schema and persists the data. That's how it rolls, right? But there is a new use case or an enhancement, and you probably have to change in the way you are fetching the data from the existing table schema itself. In those cases, in SQL world, there won't be any change to the table schema. Instead, your application uses a different SQL to fetch the data and then be with it, right? The Cassandra, it is done exactly opposite way. The table design and your consumption pattern primarily defines how you are going to have your table schema, and that's the only way application can consume the data whatever you are persisting. And that's what makes Cassandra a very fast read database, right? You have a use case to consume the data, it comes back for all the read queries. There are use cases with seconds, milliseconds kind of use cases for Cassandra for read, right? How it achieves is by starting with this, where your use case defines how you are going to consume the data, and application will consume in only that specific way. Right? Let's take the example we have, which is customer transaction, where we are just persisting all credit card customer transactions, right? And in this particular example, I have it as account number and the customer name as their key. This two makes it as a primary key, and whatever we have it as within the parentheses, that's what makes it as a partition key. And that's how data gets persisted in the disk, and that's the only way you can retrieve as well. So given this example, you provide the account number, you will be able to fetch all the customer transaction really fast, right? But that's the use case. say if there is an enhancement and you have to consume the data in a different way. For example, there is a need for you to fetch any customer transaction amount equal to 100. For those kind of enhancement, you probably may not be able to consume the data out of this. You will be able to, but that's what considered as an anti-pattern in Cassandra. Instead, you need to duplicate the data by defining the key as whatever your use case, and whomever writes has to duplicate the data in multiple places, right? It in this same, expanding on the same example, it probably is customer transactions by transaction amount, right? Then you define the key in such a way that you can fetch the data out of that. Instead, if you just want to run the same query on this table, we can still be able to do, but that's the anti-pattern because Cassandra has to fetch the data from all the partition and all the nodes in order to serve this query. That particular case is equivalent of doing a table scan for each and every query, which is not an efficient way of fetching the data. So that is where the suggestion is to duplicate the data depending on your use case. And that's what we are calling everything together as a use case defined data modeling, and how you're going to consume the data plays a major role in how you are defining your table schema, and that's the way your application is also going to consume. Okay, before we dive into the things, like want to just hit upon a few things like how we are doing things at CapitalOne, right? So CapitalOne is the first US bank to exit out of legacy on-prem data centers and go all in cloud. Right? We develop everything open source and cloud native first. And Rewards is one of such application which is built completely cloud native ground up, and that's what serves our customer, which I previously touched upon as well. If you are using any of our credit cards, everything in the backend is cloud native. And I have simplified the architecture just for easy understanding, and this is very high level representation of how Rewards uses Cassandra and all the things when it comes to the credit card transaction, right? We consume the credit card transaction and we do bunch of unrelated computation, and we persist the data in the backend data stores, Cassandra in Mongo in this case, and that's what feeds our all our backend use cases. And I have just only touched upon 2 use cases which is of significance for our discussion, right? So those 2 are enough when customer is trying to view their rewards online, or customer is getting their rewards in the statements, right? Those 2 are the use case, and we will see more in detail how we have utilized Cassandra data modeling for those 2 specific use cases. And this is a high level architecture of how we have dealt. We'll go in detail on those use cases, right? We'll start off with the real-time use case, right? As I mentioned previously, our application deals with customers' credit card transaction, and we compute the earn. And so which means there is an inherent need for customers to view their rewards online at any given point of time, right? So if you have, which is most of the case, you have a credit card, you probably log into your whomever your credit card service provider, you log into their web page, and then when you try to view online, you probably will have an option to see how much you have earned at that point of time, and you probably may have ways to redeem that too, right? So that is what one of the use case which we are dealing now. The customer is trying to log in and they're trying to view their rewards. So for those kind of use cases, we cannot do computation on the fly in the backend, and we need the data to be available to us as soon as possible, right? For those kind of use cases, it can be solved using the partition key, which is a key attribute which can identify the customer detail, right? In our example, let's say we have a table which is like the reason I have quoted few tables is we will connect all these things together when it comes to this data modeling, right? This first example is customer earned transaction, where we are having the partition key as account number alone, because account number alone can identify customer transactions. And there are additional fields which are like total earn, daily earn, all those things. But how we are defining for real-time use case is directly connected to identifiable key attribute. In this case, it's a customer account. Say an example, there is a account 123, and they have spent something on the, which is the same example we are going to discuss in the future. They have spent somewhere in the coffee store, and they spent $100, they got $10 rewards, right? And at that point of time, when customer, we have processed the transaction in our system, and when customer is trying to view their rewards, this table is what used for servicing that need, right? In that case, customer will see, hey, they have $10 at that point. This data source will persist that information in such a way that we can immediately get back the details what customer needs for real-time use case. So specifically in this, we have to see the partition key and primary key in this is defined as account number. We expand that same thing for batch use case. When you say batch use case, it's mostly like, okay, we can take some time to do this computation, and there is no immediate need to serve the request. Instead, there probably may be a need to put together some kind of aggregated data and provide that information to the customer, right? Example is statements. So typically the statements is sent to the customer for their monthly transactions, and what we need to see is how much they earned for the transaction they made in the last month, right? So that is what I mean by aggregated data. So how we can keep that same information in a slightly different way, right? Because in this case, we need the aggregated information. In order to do that, we need to keep history of what happened, but how to group them together. So we need key attribute. From the previous example, account number alone will not be able to do that. Instead, what we need to do is, the example I have quoted here is, it has the same table structure as the previous example. And there is another table we are defining, which just says as a history, but the keys are different. The keys in this case is account number, plus there is a time frame related attribute we need to have. That time frame related attribute, when you keep track of their whole history, you have a flexibility to fetch by a time frame and then do aggregation depending on whatever you need. In the statement case, it is the last month's transaction. So if you keep track of what happened for each and every day, then you will be able to fetch everything for the given customer and then do the aggregation and send it in the statements. That is the same example. So if you take the previous example, like how I was saying, account number 123 has made 2 transactions, right? So same, they bought coffee, and then for $100, they got $10 on a day. And then the next day, the same thing happened. What we will do is we will keep track of whole history in this table, but only the aggregated information goes out depending on your need, right? That's the thing I have mentioned as the aggregated view, and that's how the table schema is defined. So we want to bring home all these examples, right? And how we can connect these two together. And I have put together a sample example. And these are all the same table schemas I have used throughout my presentation, right? So there's a customer transaction, say customer Python is a coffee obsessed person like me, right? Spending something on Starbucks every day, right? They're spending 100 days. $100, and they're getting $10 earned for that spend, right? And their account number is 123. If you take that first table, that just defines their basic information. But how we are defining the next two tables is what the core topic of discussion. So when we have the customer transactions, customer has spent, in this example, 321. And at that point, they have $10 earned, and that's what they had on that day. And that's what their total at that point, right? So that was the information we have in the customer earned transactions. And the customer logs in and sees the information is fetched out of this table, whatever they have as total earned. So when customer sees, they will see as $10 is what they have. But on the other side, in their history, it probably at this point may reflect as if it's the same information, but it is persisted with a different key, and you will be able to fetch, hey, what customer has spent for a given day. It is same $10 as total earn and daily earn, right? That's how at this point it shows. When you try to pull, maybe this customer is having their statement going out on that day. When you try to go and do the whole aggregation on this, they will still see that same $10, which is what they probably will be seeing in online as well. But how we are connecting these two together for solving two different use cases, right? The process which writes to these two has to keep this data in sync, right? Whenever there is a write happening to these two tables, it will keep it in sync. Expanding on the same example, the customer is now making same transaction on the next day, 322. See how the data changes now, right? The customer earned transaction at this point, if you see the total earn, it has gone to 20, which means we keep on incrementing what they're getting as total earn. At any given point of time, your real-time facing table will have only one row for a given account. That way, when you try to fetch the information, when customer logs in, you just fetch what they have as a total and then show it, right? That way, when customer logs now on the next day, and they will see $20. That's what they have in the system at that point of time. But if you see their history, when we process their second transaction, what we are doing is we are keeping track of their history, right? So now if you see from the bottom up, you will see they spent $100 and they got $10 on that day. That was their total and daily at that point. And the next transaction has made it to 20 as their total earn. And that day they again got $10. But now we have history of their information with a time frame based query. So that table will solve the use case where you have to aggregate them by a time bound queries like statements, right? When you try to see the information out of the history table for the customer, now they will see $20, which is the same as what they will see in the real-time tool. So this is what I mean by serving them together with a different Cassandra table schemas. And that's how you need to start with your data modeling. So this is very close to the example what we have dealt. And this can be applied to any of the data which is closer to account specific things, right? What's in your wallet? Thank you everyone for the opportunity.